and Lee Yong-nam for giving me this opportunity to speak at this conference. So I had planned to spend about 10 minutes talking about the previously on log minimum model program, but Radu and Ian and David spoke a lot about the program, so let me skip that part. Or maybe just briefly talk about what it is. So the Hassett-Kill program is about the low canonical models of MG-bar. Well, Hassett-Kill program for MG-bar is the study of these guys, which is defined by project of this graded ring and and we consider these low canonical models as we decrease alpha from 1 to 0. And the principle says that as alpha decreases, these delta i's get contracted one by one in an orderly manner. And moreover, the MG alpha themselves are moduli spaces. A moduli space itself parameterizing curves with increasingly worse singularity. So judging by the work of David Smythe and Maxim Fedorchuk and Dawei Chen and also by myself, Yong-nam Lee and Brendan Hassett, MG bar and weighted pointed curve space and stable mesh spaces, they also seem to obey Hassett-Kill principle. And especially the hyperelliptic case seem to demonstrate this principle particularly well. So there's a map constructed by Writzer and Lange. It's from HG bar to V2G plus 2. This is the moduli space of binary forms of degree 2G plus 2. Forms. And what this does is it maps this sort of stable hyperelliptic curve, G minus I, and this is bias truss point. And that gets mapped to a curve of the form, a curve with y squared is x to the 2i plus 1 singularity. When I say a curve, this is the curve determined by the corresponding binary form. So what if this is smaller than that, then it's going to crush this component, and that guy becomes the resulting curve acquires a singularity of this form. Right, yeah. So when that's smaller than or bigger than that. Okay. All right. So there are actually two natural ways to consider log minimum model program for HG bar. Two natural ways. So one is to consider to be guided by K M0n bar plus alpha delta. So here I'm going from unordered case to ordered case. The unordered case, you can simply take the quotient of everything by the group of symmetric group of n letters. So if you're guided by this divisor, then you're talking about Simpson's work. So this is Matt Simpson's work. Then what you get as a result is of this program is you get a contraction. You get a series of divisorial contractions contracting these delta i's one by one. And these critical values are simply 1/2 and 2/5 and so on. So the critical values are very simple. It's 2 over k plus 2, is it? I think it is. Something like that. It's a very simple formula. The critical values are given by this simple formula. And he also shows that these spaces are isomorphic to weighted pointed curve space with symmetric weights 1 over k dot 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 1 over k. So this is Hassett's weighted pointed curve moduli space. Now another way to think about this log minimum model program is you take the following divisor. You have a map from HG bar into the moduli space, and you just pull back. Let's say this is J. Do I want J? Excuse me. No, I don't. I want eta. So eta upper star k plus alpha delta. And let's call it L alpha. Let's not call it L alpha. It's to something that's proportional to that guy. Yeah. Just to make it a log canonical divisor so that the HG bar with that guy becomes a KLT pair. So if you take a suitable multiple of this pulled back divisor, then and define HG bar alpha by the same formula, approach of the sections of times L alpha, then you don't get a picture that is quite as nice, but you still get something that's very similar to what you get in the log minimum model program for MG bar. So you, as you expect, you get exactly the same, not exactly the same, but more or less the same critical values, 9/11, 7/10. And we were hoping that we would get only divisorial contractions, but here this B4, I'll explain what this is shortly, but B4 gets contracted and other codimension 2 loci also get contracted here. So this is something that contracts a divisor and a little change. and let me see, genus 1, G minus I, G minus I is 1, is that right? Yeah. And which one, this map? Yeah, this is as an equivariant map. So you can take the quotient and pass down to M0 and tilde.
M0 to tilde, basically the hyperlocus locus.
Yes. Yeah, so if you want to run log minimum model program for HG bar, then you can do this on the ordered case and then take the quotient. Or you can start with HG bar and then take this divisor as your guiding divisor and decrease alpha.
So what is the difference between the divisors?
What is the difference? Sorry, difference between?
Is L alpha the same as Km0n plus alpha?
No, it's very different. No, it's totally different. So as you can see, you get your critical values are very different. There may be a strange formula, but I'm quite sure that they're quite different. So one reason is that you only get divisorial contractions here, and you get a small contraction and you need a flip. That tells me that they are very different programs.
So all I was saying is that because you are testing to the sigma n carbon, so the difference between the two models that there is something like a sigma n carbon, there should be some sort of correction coming from the ramification locus when you take the canonical divisor. So basically I was asking if there is some sort of divisor that can account for between the two pictures.
Divisor that yeah.
Yeah, but so there are two different divisors, but how do you form that transformation?
Okay. All right, so we'll talk later. Yeah. So, and you need a flip here, and this is also a small contraction, and you're gonna go on as in MG bar case. Now you can only say that these are birational maps and not really morphisms. This is morphism, but here you're gonna get some flips. So this is also a map that contracts B5. So why do I care about this program when I have this very nice divisorial contractions? So the upshot here is that the second program gives an outline of how the log minimum model program for MG bar and HG bar would proceed or would run. So if you compute the critical values for HG bar alpha, then those will be critical values for log MMP for MG bar. So one of the questions that I get most often is, you've got these critical values, 9/11, 7/10, 2/3, 17/28, and so on. And one of the questions that is often asked is, well, are there any patterns? do they mean something? And by working out this hyperelliptic case, I can find the formula, and I can tell you exactly which curves to discard and which curves to acquire at each step. But these are not all the critical values for log MNP for mg bar, but just a part of the critical values.
I'm sorry, when you
Yes.
write dot, 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 are
Yes.
we supposed to imagine a series of numbers decreasing to 0?
No, decreasing to, if I just look at the hyperelliptic case and compute the numbers, the limit will be 3/8.
And you can't go below that?
I think I can go below that by getting out of the hyperelliptic locus and run the whole minimum model program for whole space.
So at that point, the whole locus of hyperelliptic is going to be contracted.
Yes.
Then
Yes.
You have to done some review.
Okay. Let's answer the question. So, I mean, the existence of the minimal model program is now just the standard result.
Yes.
And so the question is to understand what's really happening. In the
Right, the intermediate low canonical models, are they modular? So I'm trying to verify this Hassett-Kiel principle for HG bar and MG bar.
But I mean, is it clear that you get kind of the same outcome?
So you're saying what?
So when you restrict to the hyperelliptic growth, is it clear that you verify the numbers? So of course you can have some other articles away from the hyperelliptic growth.
Right.
But is it clear that you get the same restriction?
The question is, if you take the thing for the whole of MG, and then you take the intersection of HG, are you seeing everything in the when you do the HG?
No, you don't see everything.
You
For
don't see
instance,
everything.
right. So there,
Intersect.
right. For instance, there's 19/29 that's in between these two, I think.
Well, maybe that's just happening disjoint from the hyperelliptic locus.
No, there's delta 2. This is where delta 2 gets contracted. And
Oh, okay.
right, so delta 2 and hyperelliptic, the ones that are hyperelliptic gets contracted at 2/3. And then the whole delta 2 gets contracted at 19/29.
So next is like what contracting hyperelliptic, and then
Right, so that's not in there, but things happen in the hyperelliptic locus first, and then probably the other locus gets contracted later on. Okay, so what do I want to do now? Okay, so here are the critical values. So so is it 2 or 1? 1 outline, critical values. So here's the formula. I can't really quite call it a theorem, but I'm going to go ahead and do it anyway. So let's show myself. So the critical values are given by this. Let's call this alpha j. So this is alpha 3 because this is where B3 gets contracted. That's alpha 4, and then it's going to go up to alpha g plus 1. So that's the last divisor, when the last divisor gets contracted. Okay. So, and I promised you that I'll explain what these B5s are, BIs are. So BIs are simply the divisors, that the divisor of the hyperelliptic curves that come from that arise as admissible covers of these curves. So you've got I points on one component and rest of the marked points on the other, and you take the admissible cover, and you either get a stable hyperelliptic curve of this form or if I is even, then you're going to get a curve of that form. So anyway, you have this pointed genus 0 stable curve, and take the stable hyperelliptic curve that is admissible cover of it, and that's what these BIs are. Right, so hyperelliptic curve critical values are given by, let me cheat, 3j squared plus 10j minus 21 7, 4, 6, 8. And you can easily check just by punching in the numbers that you plug in 3, then a quick computation yields 9/11. You plug in 4, then you get 7/10. Plug in 5, then it's 2/3. So when I first got this formula, I was disappointed because it's nothing so fancy. I was hoping that I would get some, arc sine, some transcendental functions, but it's a rational function. But that's what I get, and that's what it is.
This is a theorem about the critical values for the log n of p on hg bar.
Hg bar, yes.
Are these the same values that the check?
Sorry?
You're getting the same pictures for Rorschach, but by different methods.
Yeah, I have 2 methods to derive that formula.
J dot to G plus 1.
Right. Yes, G plus 1, even number is G plus 1 and divided by 2, and odd one G over 2. Is that right? Is it strange?
Strange way of using the bracket notation, because dividing into cases even or not.
Oh yeah, you're right. Yes. Yeah, but anyway, so there's a problem.
This can be more critical value. So this critical value are just depends on if we have only one flip for each case, but we are not sure.
Flips, so far flips did not introduce new critical values, right? So flips happen at one critical value, and that critical value plus epsilon, then you get one contraction.
Using the one contracting divided with the codimension 2, then flip, and then you considering no more impact.
Right. So I could get more critical values, but those are, if this principle is correct, then those are surely critical values for HG bar and MG bar. That much we can say, I think. Okay. Now, and so that's the formula, and I also have the log discrepancy formula, which tells you how the divisor changes. So you've got the map from HG bar to HG bar, G bar, alpha J, and let's call this map FGJ. And you have L alpha here, and the psychotheoretic image, if that is the correct word, and let's call it, and then you pull it back. So FGJ upper star of the image of Does that make sense? I want to say psychotheoretic image. Is that okay? On Hg bar alpha j. Let's say this is L alpha j bracket. Then it is related by, it is given by R2 K choose 2 BK tilde. Let me flush out R2. K goes from 1 to J plus and rest of the stuff. K goes from J plus 1 to G plus 1, where L alpha, these R's are just the coefficients of the original divisor L alpha. L alpha is Rj or RK BK tilde. From 1 to G plus 1. And if you're curious, I can write down what these are. And I'm going to assume that you are curious and actually write it down. 13 over 4g plus 2 sg plus 1 minus s plus 2 alpha minus 2. It's pretty terrible. And the odd ones one thing that I want to point out in this formula is that this really depends on the G, genus G. And if you look at the critical formula, and that does not depend on G.
So who is S?
Oh, S is the variable, parameter. S goes from 1 to G over 2, G plus 1 over 2. Is that right? Yeah. So S is like K here.
Is there really a minus S in that?
That guy? S times, right, S times G plus 1 minus S. And that's S times G minus S, not 2. Yeah. All right, thanks. All right, now once I have this log discrepancy formula, then I can easily derive the fact that the last log canonical model is isomorphic to the binary form space. That B is got nothing to do with the B tilde. It's just binary form space. Now, why is it obvious? Because if you plug in L alpha G plus 1, that guy, you replace all these Ri's by K choose 2. Then you get something that is proportional to K choose 2 BK. And this is the linearization that comes from the symmetric linearization on this binary form space.
So that's a stable form. The B2, that's just forms of W2 G plus 2.
Yes, exactly.
And regardless of where their zeros are. They can have as many multiple zeros as they like.
Well, it has up to half of 2g plus 2 many. So g plus 1 many is multiplicities.
Yeah.
Right, semi-stable. Yeah. So once I have this line bundle formula, then it's easy to see that these two are isomorphic. Because you get this by contracting the divisors delta i's. And here all delta i's are contracted, so they are isomorphic up to codimension 2, away from codimension 2 locus, and they have the same ample line bundle. So therefore they are isomorphic. Okay. Now, so the key here was to figure out what this log discrepancy formula was. Before that, we did some computations in low genus case, and that takes a lot of work. It's a lot of combinatorics. But once you have this log discrepancy formula, then deriving that critical value formula is very easy, as you will see. So key is to figure out the log discrepancy formula. And once you have this, then Hassett-Kill principle says FGJ contracts BJ tilde, right? Now let's assume that things are true for j minus 1, so that L of j minus 1 is given by what it is. Then what I'm going to do is I'm going to take the intersection of this guy with this a, b, j minus a minus b. This is vital curve in bj tilde, and it looks like this. So these are all genus 0 curves. There are b many points, and there are b many points, and then there are j minus a minus b many points, and then the rest of them are here, and then there are a points. Now this is not a one-dimensional, nice one-dimensional curve. So when I say there are b points on this component, it really means that you break it into 1 point, 1 point, and you go on and on like that, and then 1 point. And on the last component, you just put 2 points to stabilize. Then you move one of these attaching points, then you get a curve, and that's the vital curve associated to C, A, B, J minus A minus B.
So that's just the device to make sure you have a zero-dimensional.
Yeah, right, exactly. Yeah. One-dimensional locus. Yeah, one-dimensional locus. Right. So you take this vital curve, and that's in bj tilde, and every curve in bj tilde, not every curve, but if this is 0, then the morphism associated to this divisor is going to contract every curve that is equivalent, numerically equivalent to this curve. So Hassett-Kill principle says that FGJ is going to contract bj tilde. And I'm just going to set this intersection to 0 and then compute alpha. And this intersection is given by the powerful formula obtained by Kill and McKernan. And it is just R. I'm going to put J minus 1 to denote that it is the coefficient of L alpha J minus 1. A plus B are A plus C. C is J minus A minus B. R C plus B minus RA RB RC minus RJ, I think. Is it? Yes, RJJ minus 1. Now, before, when we did not have this log discrepancy formula, then you can imagine that you have to work with these coefficients. And you have to plug it in there and then compute where the zero of that formula is. And you have to do it for every, a lot of vital curves like this. So it's a fairly complicated mess. But once you have that log discrepancy formula, then you just realize that all these guys are less than J. Actually, strictly less than J, except that one. So everything is replaced by K choose 2. So it's now the computation looks doable. It's R2 times A plus B choose 2 plus A plus C choose 2 plus B plus C choose 2 minus A choose 2 minus B choose 2 minus C choose 2. And then I'm going to subtract off J choose 2 minus J choose 2 and then add it. J choose 2 R2 minus RJ J minus 1. And if you're quite smart, you realize that this is 0. It's simple combinatorics. That's 0. So there's really not much computation going on here. So the critical value is given by R2 minus RJ. Now you can substitute those complicated coefficients in here and get your critical value. You set this equal to 0 and get alpha j. So once you figure out the discrepancy formula, and with this simple combinatorics, you can quickly figure out what this critical value is. The most amazing thing about this program, in my opinion, is the strong interplay between this intersection theory, birational geometry, and GIT. So what I'm going to do now is to derive the critical value formula by using GIT. So by analyzing stability of certain curves, I can get exactly the same formula. So Hassett-Kill principle predicts that as you run this minimum order program, this guy is replaced by curve of that form. So if this is C, then this is the curve normalized, but this bracket means that the curve is normalized by CG minus I, and you're putting singularity at this attaching point. Then you get this curve, and that's what Hassett-Kill principle predicts. Now, if, this is a big if mg alpha or hg alpha, let me just say mg alpha, or I change my mind, is indeed or can be constructed as a GIT quotient, then it means that at these critical values alpha i's, the stability of these curves go from stable to unstable and unstable to stable. The stability of these curves changes at alpha I. But what do you mean by at alpha I? How does this alpha I come into play in GIT? And the answer is linearization, which has already been mentioned in Ian's talk. So the alpha, the parameter alpha comes into play in the linearization in GIT. That's a strange sentence, but I hope it's okay. So a GIT quotient depends upon how you linearize the variety, and that's where the parameter alpha comes into play. So let me quickly recall what Ian wrote down a couple of hours ago. So you've got this Hilbert scheme, G nu into P bracket P of M SM V star. V is how this is where the curve is embedded. C is in P of V. Excuse me. Then phi of Vm upper star. You pull back the O1, then this is proportional to 6m nu squared minus 2m nu minus 2 nu plus 1 lambda minus m nu squared over 2 delta. Okay, so you've got this parameter m and nu, and I'm going to fix nu as 2. If I put 2 in here, then I'm going to get a family of linearizations parameterized by m. Okay. So on the other hand, now you've got this birational map from Hilbert scheme to the moduli space mg bar, although I'm talking about hg bar there apparently. Then if you pull back k plus alpha delta, then it is equal to 13 lambda minus 2 minus alpha delta, right? And it is actually proportional to this line bundle when m is equal to, let me cheat again, 3 times 2 minus alpha and 2 times 7 minus 10 alpha, or alpha is 14m minus 6, 20m minus 3. So you've got this one-to-one correspondence between m and alpha. It's not one-to-one correspondence for every m and alpha, but for meaningful m and alpha, for us, it is a one-to-one correspondence. So you can say alpha Hilbert stable, which means the curve is m Hilbert stable for the corresponding alpha. So this is how alpha comes into play in GIT. Now what I'm going to do is I'm going to analyze the stability of the following curve. The curve obtained by taking a genus G minus I curve and then put a rational curve R. This is rational. This genus is it's normalized by genus 0 curve, and here it's got this singularity, and then this guy has a parametrization. So R can be parametrized. Now, once you have the parametrization, then you can easily compute the lowest weight with respect to the following one parameter subgroup. So with respect to one PS row with weights coming from automorphism of R, and I'm not even saying what this parametrization is. I'm not even saying how I choose my coordinates to diagonalize my one parameter subgroup action. But let me just write it down. This curve is C0, and C0 M rho is equal to, let me cheat again, 1/3 m minus 1 4 I squared minus 8I plus 2 m minus 3I squared, which is equal to 17 alpha minus 8 over 8 times 7 minus 10 alpha squared, 8j squared minus 8j minus 4, alpha minus 3j squared plus 10j minus 21. So this is exactly the critical value alpha j. Now what's I and j? Well, I is that I, and here I'm using j is 2i plus 1, and alpha is equal to that guy. So if you just make this substitution, then you get this Hilbert-Mumford index as something positive times something times alpha minus alpha j. So this means that the Hilbert stability of the curve flips, it's a bad word to use, at alpha j. Yes?
Did you try to write this formula in terms of the local interpretation?
No, I have not. But
Sorry?
I have not. Yeah, the answer is no. Right.
I was wondering.
No, but look, that's what he's saying, that something which is a threshold, which is a flipping value, a threshold for the log minimum one program, is also a threshold for GIT. I mean, that's at least a spirit.
Yeah.
Given that we know it's otherwise stable on the top value, right?
Right. Well, this is actually not stable, so that's not the real story here is that if you analyze the deformation theory of the curve, then that curve is G minus I, this thing, and that's actually has got to be bias truss point, and that has got to be a hyperelliptic curve. And this specializes to my curve C0 and C1. And the other thing specializes to that curve along rho inverse, which means that that guy goes from stable, which is true, to unstable at alpha j, and this does the opposite. It used to be unstable, but now it's going to be stable. So this strong interplay between birational geometry and GIT gives an outline. The outline is by analyzing the intersection theory, you get the critical values where you know that the low canonical models are going to change. And by analyzing this GIT, you know which curves to discard. At alpha j, you discard this and buy this curve and put it in there. Okay. So that's the outline part. And now I've got to do genus 4 case, but unfortunately I have only 5 minutes.
Can you just mention the result for genus 4?
Yes, let me just write down the theorem then. Oh, by the way, everyone seems to forget to make proper attributions. So this is joint work with Brandon Hassett and Ian Morrison, Yongnam Lee. Yeah. This particular genus 4 case is joint with Yongnam Lee. So it's a new theorem. So there is a proper birational morphism. I'm going to call it phi from M4 7/10 minus epsilon, which is isomorphic to M4HS. So M4 2/3 with exceptional locus is bias truss genus 2 tails. It's something that many of you probably know already. It's even mentioned in Ian's talk. So it's got G minus 2, genus 2, and that's bias truss. And we also show that proof that it is isomorphic to two-thirds for alpha between 2/3 and 7/10. So 2/3 is actually the right next critical value. Is that strange?
It's
So
changing
the
at
second
2
one
over 3.
2 over why? Well, 2/3 is isomorphic to 2/3. I think it's fine.
No, at 2 over 3, then it's contracting with this.
Oh yeah, you're right. Yes, you're right. You're right. Then this has actually got to be 7/10 minus epsilon, right? Yes. Sorry. You're right. Yep. There you go. So.
And that one is
Right. This is right. Right. This is H semi-stable moduli space. And we are pretty sure that. Sorry, I'll address your question soon. This is actually point. Yes,
No, I was asking about the second part.
the second one.
Four or M2?
Yes, G is 4. Sorry, G is 4. Thank you. But we are almost sure that we don't have the GIT for this 2/3 yet, but when we have the GIT, we'll have this isomorphism.
And do you have any idea what are the typical speed below 2/3?
Below 2/3, well, you can generate the numbers by using the formula that I gave you. Is that what you're asking?
No, no.
Yeah,
The
I mean,
other
at
principle is difficult because we already after then contrast the hyperlogic and then this one we can.
Oh, for M4.
for M4.
Yeah, for M4, that's difficult. So M4, the hyperelliptic locus gets contracted, and then something and some other divisorial contractions may happen. And if you're wondering about then that's a difficult thing to understand. As in that. Yeah, we do have some values, right?
There is some theorem from circuit theory. If you have some vibration, this surface vibration has a vibration, this general curve does not belong to that amount. So there is a kind of inequality for slow to make it better.
All right, thank you very much for your attention.